Welcome to the Explainer. Today, we're diving into the high-stakes, completely hidden world of firmware validation. We're going to unpack the incredible engineering that ensures the devices we literally rely on every single day actually function safely and securely long before they ever even reach our hands.
Think about it for a second. What invisible nervous system actually controls your smartwatch, your car, or even the servers running the entire internet? Well, it's firmware. And while we expect our smart devices to be perfectly reliable, the foundation they run on is notoriously complex to build and even harder to secure.
So, here's our roadmap for today's Explainer. We're going to start with the firmware complexity crisis, look at how the industry is shifting validation left, explore automated firmware analysis, uncover a shocking blind spot in the update attack surface, and finally, wrap up with how we're securing our connected future. Let's get into it.
All right, Section 1, the firmware complexity crisis.
You see, the demands placed on modern firmware have completely outpaced traditional engineering timelines. The teams building these systems are facing some massive challenges right now. We're talking incredibly high architectural complexity, all mixed with really short, high-pressure time-to-market schedules. Plus, firmware is coded at a very low level, often including tricky, totally unforgiving inline assembly. But the absolute biggest historical bottleneck? Development has traditionally been gated by physical hardware availability, meaning you literally couldn't test the software until the physical silicon chip was manufactured. Talk about a roadblock.
Because hardware and firmware teams have entirely different needs, we end up with a major debug trade-off. Traditional simulation gives you the exact bit-level accuracy you absolutely need to debug physical chip designs, but it is way too slow to run firmware. On the other extreme, virtual platforms give you that lightning-fast execution speed for software development, but because they use abstract hardware models, they just aren't suitable for deep hardware debugging. It's a classic catch-22.
Which brings us to Section 2, Shifting Validation Left.
To break this brutal hardware-software bottleneck, industry leaders like Intel had to fundamentally rethink their development timeline through a really cool concept called shifting left. In the old days, firmware development couldn't really start until physical silicon actually existed. But to meet modern demands, the industry is literally shifting firmware development and co-validation much earlier in the timeline. They do this by using virtual prototyping. This allows software to be tested on simulated hardware before a single physical chip is ever printed. Pretty amazing, right?
So the crucial point here is the massive contrast between the old and new ways of doing things. The costly old method of waiting for silicon meant finding bugs very late in the product lifecycle, and that makes them incredibly expensive to fix. The new standard, however, leverages early parallel development. By using tools like System C, which is a specialized modeling language, and abstract hardware models, engineers can validate hardware and firmware together. The result? They catch those complex bugs early and much more cheaply.
Now, to actually make this early validation possible, engineers use what are called transaction-level models, or TLM for short. This creates an early, abstract bridge between the hardware and the software. Instead of obsessing over individual electrical signals, TLM captures higher-level units of work, like a specific memory read or write. This totally breaks the sequential dependency, freeing up both teams to build and test their logic concurrently. It's a real game changer.
But how do you manage this across massive systems and ensure everyone is actually on the same page? Well, Intel developed a framework called iPave. Step 1. Architects capture complex protocols using visual I-flow diagrams. This creates a super easy-to-understand contract between the hardware and software teams. Next, these visuals are automatically compiled into formal logic sequence diagrams, or LSDs. Finally, as the firmware actually runs, they co-simulate the system traces against these LSDs. If the actual execution deviates from the formal specification even a tiny bit, the system flags it immediately.
All right, let's move right along to Section 3, Automated Firmware Analysis.
Because firmware operates at such an incredibly low level, your standard run-of-the-mill testing just doesn't cut it anymore. Automated analysis tools are stepping in to supercharge validation. Engineers deploy two main strategies here. First, dynamic testing. This actually leverages those transaction-level models we just talked about to intelligently generate tests and monitor the interface while the code is actively executing. Then, on the other hand, you have static checkers. These are fascinating because they analyze structural code properties like memory safety and timing without actually running the firmware at all. Mind-blowing stuff.
A really powerful example of this static analysis is symbolic simulation, using a tool known as CBMC.
So instead of testing a program with specific individual inputs, CBMC treats inputs as mathematical symbols and exhaustively checks every single possible execution path in the code. For instance, researchers actually applied this to Samsung's 1NN NAND flash controller. They looked at these deeply nested loops and exhaustively validated that the data was being read correctly at a bit-precise level. It catches those tiny, obscure errors a human would easily miss.
Another absolutely crucial application of formal analysis is managing interrupts. In embedded systems, programs are constantly being interrupted to handle urgent tasks. It's just part of the job. But if an interrupt is interrupted by another interrupt, a simple programmer error can cause the system stack to grow unchecked until it completely crashes. This is a chaotic event known as an interrupt storm. By using automated model checking, engineers can definitively prove that the code is safe and will never trigger these fatal, cascading errors.
Next up, Section 4, the Update Attack Surface. We really need to examine a critical and honestly often overlooked blind spot: the very update mechanisms that are meant to keep our devices secure in the first place. There's a sobering fact from a recent Usenet security paper revealing that firmware updates themselves have actually been recognized as one of the top 5 security risks for embedded devices. Yeah, you heard that right. While designed to patch vulnerabilities, a poorly implemented update mechanism can introduce entirely new attack surfaces, allowing adversaries to execute arbitrary code or even force the device to roll back to an older, vulnerable version.
So, what exactly are we dealing with? Well, these firmware update vulnerabilities are quite unique. Unlike standard memory corruption bugs, these flaws stem from incomplete or incorrect verification steps across the complex update path. We're talking about fundamental, logical failures here. Things like completely missing a version check, failing to verify cryptographic signatures, or relying on totally outdated algorithms like MD5 to check file integrity. It's like locking your front door but leaving the key right under the mat.
To combat this massive issue, researchers developed an elegant, automated tool called Checkup. Because update procedures often span multiple languages, bouncing back and forth between web front ends and compiled binaries, Checkup first generates what's called an inter-process update flow graph. This slices right through the complex code to map the entire execution path. Second, it recognizes verification procedures by matching the semantic similarity of data flow graphs, or DFGs. Finally, it dynamically validates its findings using firmware patching to ensure these alerts aren't just false positives, but actual exploitable threats.
And the real-world impact of this automated methodology? It is staggering. By running Checkup across 12,000 real-world firmware images, researchers discovered massive security gaps. We're talking the assignment of 25 official CVEs, which, if you aren't familiar, are publicly disclosed assigned cybersecurity vulnerabilities. This included brand new zero-day threats found across 33 different device families. It just goes to prove exactly how vulnerable these update verification chains truly are out there in the wild.
Bringing us to our final stop. Section 5, Securing Our Connected Future. To summarize how all these combined engineering efforts are actively securing the backbone of our digital world, let's look at our key takeaways from this explainer. First, firmware complexity absolutely requires shifting left. Catching bugs early is non-negotiable now. Second, the old wait for physical silicon has successfully been replaced by virtual prototyping and early co-validation using models like System C. Third, to ensure absolute reliability, engineers are relying heavily on automated symbolic analysis, like CBMC, to exhaustively check that low-level C code. And finally, we must recognize that over-the-air updates are a major attack vector, requiring rigorous, automated tools like Checkup to map and secure them properly.
Which leaves us with this final thought to ponder. As engineers continue to shift left, and these automated tools map and verify our deepest attack surfaces in real time, how long until zero-day hardware vulnerabilities become a complete relic of the past? Or on the flip side, is the complexity of our connected devices scaling faster than our ability to actually secure them? It's a wild arms race for sure. Thank you so much for joining me on this explainer. Keep learning and stay curious.